Citations.
All right, well, thank you for that introduction, Dr. Kimmerite. And as he said, my name is Nick Hurdle, and I'd like to discuss with you all today the response of non-irrigated peanut to multiple rate-delayed flumioxazin applications. For the 2020 growing season, our Georgia peanut growers harvested nearly 324,000 hectares of peanut, totaling about 1.49 billion kilograms. This averaged out to be about 4,600 kilograms per hectare of the predominantly runner type peanut. And of those hectares harvested, about 70% of them were non-irrigated, with about 30% of them being irrigated. It is crucial that our Georgia peanut growers manage weed species and control weeds within their fields for a profitable growing season, especially during the critical control period from week 3 through week 8. And we believe it is better to prevent a weed infestation than it is to react to one. And this prevention can be achieved through the use of pre-emergent herbicides. One of those pre-emergent herbicides is flumioxazin. So flumioxazin is classified as a group 14 herbicide or a protoporphyrinogen 9 oxidase inhibitor. Flumioxazin controls numerous broadleaf species as well as some grasses and requires about 0.64 centimeters of water for activation. The label states that flumioxazin should not be applied more than 2 days after planting, and the full peanut application rate is 107 grams of AI per hectare or active ingredient per hectare. But there has been some studies shown that flumioxazin can cause injury under non-favorable conditions, such as cool soil temperatures matched with rainfall. And other studies also show that irrigation or rainfall and herbicide application timings are critical to injury severity. Price et al. In 2004 noted a 40 to 60% injury when irrigation was applied 12 to 14 days after the flumioxazin application. And Johnson et al. In 2006 noted a 59% injury when flumioxazin was applied 10 days after planting. But the main thing with these studies is that they were maintained under irrigated conditions. So these previous studies set the premise for our non-irrigated study. The objective of our study was to quantify the flumioxazin injury on early season peanut growth when applied pre and post-emergently under non-irrigated conditions. The hypothesis for the study is that the flumioxazin injury will increase as application timing after planting increases as well. This study was performed in 2020 and 2021 using cultivar Georgia 16HO in Plains and in Tifton, Georgia. For the design, again, we had 2 locations. We had 4 herbicide rates at a 0 or a non-treated control, a quarter rate, a half rate, and a full 1x rate as indicated on the image on the right. We had 6 application timings at 0, 3, 5, 7, 10, and 14 days after planting. We had 4 replications per treatment set up in an RCBD design. And the main thing to note about this study is that it was maintained under non-irrigated conditions. Data collected included stand counts and plant widths, percent injury to the non-treated control, weed control, and weed counts for nutsedge, morning glory, and sickle pod, as well as final yield. But for the purpose of this presentation, we'll only focus on percent to the non-treated control as well as final yield. Data were analyzed using Tukey Kramer HSD for rate, timing, and rate by timing interactions set at an alpha of 0.05. Data were separated by year and location, and only the 2020 data will be presented. One thing to note is that there were 6 total ratings for injury taken, but only the first 3 ratings after each flumioxazin application were used for analysis. So let's move into the results. For Tifton, Georgia in 2020, across the x-axis, we have the days after planting for the flumioxazin application. And along the y-axis, we have the average injury as a percentage. The green bars indicate the 0x rate or the non-treated control, orange are the quarter rates, blue is the half rate, and pink is the full 1x rate. This graph indicates to us that the later that the flumioxazin is applied after planting with a higher rate, the more injury that the peanut plant sustained. For yield in Tifton for 2020, again, days across planting or days after planting for the herbicide application across the X, and yield in kilograms per hectare along the Y-axis. This graph indicates to us that the only differences noted were with the full rate applied 14 days after planting when compared to the applications made at planting. For Plains, Georgia, again, days after planting for the Flumioxazin application on the X and average injury as percentage along the Y. Orange is a 0x rate, blue is a quarter rate, red is a half X rate, and the yellow is a 1x full rate. Again, same trend as noted in Plains that was in Tifton. The later that the Flumioxazin is applied at a higher rate, the more injury was noted. For yield in Plains, there were no differences noted for the 2020 growing season. So let's revisit our hypothesis that the Flumioxazin injury will increase as application timing after planting increases. We will fail to reject the hypothesis due to the injury as rate and days after planting for the herbicide application increased, injury increased as well. And for yield, the differences again were only noted in Tifton with a higher rate and later application equaling a decreased yield. As far as control, that's the full rate applied at planting had the greatest control. But how can we mitigate this injury? What are some options that we can implement? One would be to adopt the 4 R's of fertilizer best management practices, such as applying the herbicide at the right place, at the right time, with the right product, and at the right rate. Others would include following agronomic practices such as planting at a proper planting date, using high quality seed, as well as proper irrigation. But what about before the seed is ever planted? Do seed storage conditions and seed treatments have an effect on early season peanut vigor that could help the plant overcome these early external stresses? But before we can answer that question, we need to know, do these seed storage conditions as well as seed treatments affect seed germination? So what exactly is the purpose of seed storage? It is to slow the process of deterioration or the changes over time that affect the seed's ability to overcome those external challenges. And this can be achieved by utilizing a stable temperature between 1 and 5 degrees Celsius with a stable humidity between 55% and 70% and proper aeration in those storage conditions. What about seed treatments? They are utilized to control the seed surface-borne and seed internal fungal pathogens, as well as the soil-borne pathogens. In a brief history on some seed treatments, the first one was a brine solution used in 1637, followed by the revolutionary Bordeaux mixture in 1885, with the current seed treatment being a drier dust such as Rancona or Dynasty. And an up-and-coming player would be a polymer coating, which has been adapted from the pharmaceutical industry. So the objective for this study was to quantify the treated and non-treated peanut germination response to stable and variable storage conditions. The hypothesis for the study is that the polymer treated seeds stored in the variable storage condition will deteriorate faster than the polymer treated seed in the stable condition. For this study, we utilized the cultivar Georgia 07W treated with nothing for the non-treated control, Rancona VPD dry, Rancona plus Slip Shine 6300, and Rancona plus Slip Shine 2050, and the Slip Shines are the polymers. For the storage conditions, we placed these seeds in a stable storage conditions ranging from 20 to 22 degrees Celsius at 50% humidity, and a variable storage conditions at 22 to 49 degrees Celsius with a humidity ranging from 15 to 100%. The seed remained in these storage conditions for 6 weeks. We then took the seeds out and placed them in a petri dish with 10 seeds per dish and placed them on a thermal gradient table with temperatures ranging between 13 to 32 degrees Celsius with 216 dishes per table. We watered the seed with 10 milliliters of DIL water at the beginning of the study and supplemented as needed. We left the seed on the table for a total of 7 days with counts beginning on day 3. We had 2 replications per treatment per storage condition for the duration of the study. This image indicates the different treatments with the 2 polymers on either side of the non-treated in the middle with the Rancona dry on top. The data was analyzed, so we wanted to determine the GDDs needed for 80% germination, so we utilized the Freund and Littell equation from 1991. where the B0 is the upper asymptote, B1 is the relative slope, XP is the value of X or GDDs needed when Y is at P% of the upper asymptote. This study, we used 80%, with Y being the percent germination data. This data was then graphed in sigma plot 14 with a separate curve fit for each seed treatment and storage condition, with the cumulative germination at 168 hours after initiation. The model also indicates the minimum temperature for germination at 168 hours. So let's move into the results. Across the x-axis, we have the growing degree days, and along the y-axis, we have the cumulative germination for the initiation or for the start of this test. This graph indicates to us that all seed did have an initial germination of at least 70% before being put into the storage conditions. This graph is for 6 weeks after storage, again, growing degree days across the x-axis and cumulative germination along the y-axis. This graph indicates to us that all variable storage seed germinated lower than any and all of the stable storage seed, with the 2 polymer treatments in the variable storage not fitting the model. Here we can see the actual number for the maximum germination at the initiation of the trial on the table on the left, compared with the maximum germination rate for the 6 weeks in storage for each treatment. The numbers in red indicate the percent change over 6 weeks for germination with the respective initial germination rate. And again, the 2 polymer treatments did not fit the model for the variable storage conditions. So let's revisit our hypothesis that the polymer treated seed and seed stored in the variable storage conditions will deteriorate faster than the polymer treated seed in the stable conditions. We will fail to reject that due to the variable condition seed did deteriorate faster than the controlled condition seed, with at least a 28% reduction in the variable control seed. As well, again, the polymer treated seed in the variable storage conditions did not fit the model. So for future research, I'd like to perform the study on the new release additional polymer treatments, as well as on additional peanut cultivars, as well as potentially switching from sampling on day 3 to beginning on day 1 after watering. Here's a list of citations used throughout this presentation, and I'd like to thank my committee members, as well as University of Georgia, my fellow graduate students of Juliana Rodriguez and the now Dr. Kayla Eason, as well as the Georgia Peanut Commission, as well as the National Peanut Board. And I thank you for your time, and with any remaining time, I'd like to answer any questions you might have.
Thanks, Nick. We have plenty of time for questions.
So there's some up there.
Okay. The first one comes, are you able to hear me, Nick?
Yes, sir, I am.
Okay. First one comes from Dr. Cristiane Pilon. Nice presentation, Nick. I may have missed the information. Where did you store the seeds during the 6 weeks, and why did you choose this cultivar?
Okay, so the question is, where did we store those seed during those 6 weeks of storage, and why did we choose this cultivar? So the seed were stored in a lab setting with a controlled temperature and controlled humidity, and another variable storage was in a greenhouse that, fluctuated from 15 to 40 degrees Celsius in a large range of humidity percentage. And we chose that cultivar because that's what was handed to us from the polymer industry, from what the polymer treaters used.
Okay. Second question is from Peter Dautre. Nick, good presentation. If Valor is applied post to the weeds, do you think growers would include an adjuvant? Do you expect more injury to the peanut? Thanks.
So the question is, if Flumioxazin or Valor was a treat or had an additional adjuvant added with the tank mixture, would that be more injury to the peanut plant? I would think it would be. As far as how much, I don't exactly know, but I think there would be an additional injury to the peanut plant. And the label states that it should not be applied more than 2 days after planting. So, 2 days, the peanuts are still imbibing water and starting that germination process. But to answer your question, I think there would be additional injury to the peanut plant with the added addition of an adjuvant.
Okay. Last question is from Dr. Culbreath. Were rainfall patterns similar for Plains and Tifton, or were they typical, quote unquote, for non-irrigated fields in most years?
So the question is about the rainfall that occurred during the rating times, and in Plains, it was about Tifton received about 2.5 or more times the amount of rainfall during the rating times. I think Tifton received about 18 centimeters or so, and Plains received about 7 centimeters or so. So that explains the amount of injury that was different between the two locations.
All right. Well, thank you, Nick. That's the time we have.
All right, thank you.